a, a decirnos a decirnos cómo un editor optimiza su tiempo y que si tu paper es una mierda, posiblemente a no ser que pongas a alguien que, bueno, que no lo van a leer.
¿Y quién hacía el curso?
Sofía, espera, es una mujer que da también terapia en el CFM y que es psicóloga, pero que está especializada en gente que trabaja en ciencia.
Pero en el curso que os han enseñado más o menos.
Pues la estructura de... Mira, la mujer se llama Sofía Facal-Belli.
Vale.
Y nos han enseñado pues la estructura que debiera de tener como pues, un abstract y un paper entero. Nos ha dado tips muy interesantes también de cuál es todo el proceso de submission de un paper. Eso, vino Javier Aizpurúa para decirnos un poco cómo era desde el otro lado, desde el editor. Nos dijo que lo más importante era título, abstract y cover letter.
Bueno, depende también del campo. Por ejemplo, nuestro campo cover letter da igual.
Ya, eso es lo que estábamos también...
Da igual, es que yo no sabía ni que existía una cover letter.
Tampoco.
Yo nunca he escrito cover letter.
Pero sí que había muchas cosas y, claro, Laura y yo estábamos en plan, no sé yo si esto aplica tanto a nuestro campo.
Muchas cosas era teórico total.
O mucho
Si escribes
outsourcing.
un paper al mes, pues igual eso te sirve, pero...
Claro, y mucho eso de outsourcing también, de quién aporta en qué, no sé.
Sí, nuestro campo es muy diferente.
Por ejemplo, o sea, la estructura también de un abstract era mucho como Introduction al Field, Knowledge Gap, y luego, pues, qué es lo nuevo que aporta, pues que se puede adaptar a lo nuestro, pero muchas cosas que son de análisis, characterization.
Sí.
Pero bueno, está bastante bien como para tener una estructura sobre la que basarte. Y lo que lo hace todo.
¿Somos 4?
Los
A lo mejor Juan viene. Los ingenieros que vengan, los ingenieros te van a matar.
¿Y Samuel?
Bueno, escríbele.
Pero los cosmos creo que vienen también.
Sí, me ha dicho.
Para el café antes y me dice, estoy en el laboratorio, creo, haciendo cosas.
Creo. Estoy en mente. ¿Cómo era Fiscally?
Fiscally here. Voy a mandar un mensaje en el grupo.
A nivel de tiempo, me mandaste un mail, pero no me acuerdo. En total, ¿cuánto más o menos?
50 minutos. Más preguntas.
Vale, no, iré tuneando más o menos. Vale. Ok.
Juan preguntaba, ¿recomiendo poner Juan para comer?
Yo he resuelto las 6.
Las 6.
Pero bueno.
Eso es Juan, eso.
Será eso.
Claro.
Y bueno, ¿has conocido a los estudiantes ya?
No los estudiantes.
¿Cómo que no? Francesc, sí.
Estaba con Francesc y sí.
Es un buen estudiante.
No, quiero decir, perdón, Francesc sí, los estudiantes no.
Exacto.
Entonces es muy buen estudiante.
Bueno, está haciendo un estudio largo, ¿no? Entonces.
Sí, eso sí.
Pues Mariana, encantada.
Encantado.
Sí.
¿Laura?
Yo por.
Encantado. Bueno, estupendo.
Marian y Pablo, bueno, Pablo acaba de empezar, pero están más en la parte de Next
Sí.
y de, bueno, desarrollo de PCs. Laura está trabajando en un proyecto sobre un nuevo tipo de PET con cristales de URT.
Sí, esto es justo, lo he visto antes en Labs. Simul.
Sí. Para una idea, Marian sería cigarro,
Vale.
Laura sería los cristales de PET.
Sí.
Y Pablo sería el proyecto que está en Miramón, que no te hemos enseñado.
Vale, sí, ok.
Más Next. Y Samuel, por desgracia, ya le conoces.
Sí. ¿Y hay un poco de todos? O sea, ¿todos hacéis un poco de los otros proyectos o es más...?
No tanto.
Ok, bueno.
Bueno, lo de Pablo y mío es bastante parecido.
O sea, para empezar, se va a hacer la simulación del detector Zeus en Miramón y se va a basar en el trabajo que ha hecho María. Pero, por ejemplo, lo que hace Laura, que es un poco más diferente del resto de instrumentación, aparte de gases, pues no hay tanta conexión.
Ok, ok, ok.
Sí. Vamos a esperar unos minutos. Perdón, estoy sentado porque tengo dolor de lumbar.
Sí, es así.
Sí, sigo. No, sigo así desde el otro día.
Pero, ¿sea un fisio o algo?
No. Yo no creo en esas cosas. Eso,
No está en el dolor, entonces.
eso es como el resfriado. Si te cura, te dura una semana. Si no te curas, te dura 7 días.
Good luck.
Igual. La lumbar es igual. Si te curas, dura una semana. Si no te curas, dura 7 días.
Es tu lumbar, no la mía.
Voy a cerrar ahí. Mejor. A ver si no. Vamos a esperar un par de minutos y empezamos. 5 minutos académicos. Justo ahora han empezado a cortar.
O sea,
Bueno. 3. Así se ve. ¿No?
Por ruidos.
No sé.
Mejor.
Este. Sí. No os vais a dormir, ¿no?
O quizá.
¿a qué venimos si no?
¿Mm?
¿A qué venimos si no?
Una buena fiesta.
Esta luego tenía problemas. Tienes vídeos.
Bueno, un par de animaciones sencillas, pero...
Bien. Well, I think we can get started. So I'll start first with the introduction of César. So César is a postdoc at CERN. He's a researcher there. He specializes in neutrino physics. He did his thesis at the Autónoma University of Barcelona. And actually, his thesis got the prize from the Royal Society, Spanish Royal Society of Physics for the best experimental thesis in particle physics. He works in the T2K, hyper K, super K experiments. And he's going to talk a little bit about a new way of simulating physics detectors, in particular about this concept called differentiable simulation. We will try to introduce a new way of doing this seminar. So I talked before with César, we will try to do a first half more general, even for people who are not very familiar with neutrino physics detector. And then the second half, going a little bit more in detail regarding neutrino physics and what are Cherenkov detectors.
Right.
So thank you very much. And yeah, let's get started.
Yeah, thank you. So yeah, I see that you have done your research. Yeah, so it's a pleasure for me to be here, like getting to know like some other people working in related concepts, even if like we don't work exactly in the same experiments. So this seminar is about, let's say, a new technique, these kind of like differentiable simulations, which I think that really are very powerful new ways of, let's say, calculating things that many experiments, let's say, have in common. And I will be focusing in particular to one thing that is very close to my specialty, let's say, this kind of optical detectors. But really, many of the things, many of, let's say, the benefits of this technique, it's something that would benefit other experiments, just like adjusting the things that are different across them, right? So, okay, in this talk, as Roberto said, like, okay, we can discuss a bit. So I prefer that if you have a question or at some point you feel a bit lost, like just like stop me, make a question like on the spot, and then we can clarify these kind of things. Because, okay, so at the beginning, I will be like kind of like very general, trying to explain like why I think that this kind of thing is cool. Then I will jump into a bit more like technical parts. I might go quicker there if I see that some of the people start falling asleep. And then essentially, okay, maybe some nice plots at the end and things like this that are a bit better to follow. So kind of like the concept, no? So I'm focusing on these optical particle detectors. So let's be sure that we're all kind of like aligned in understanding what these detectors are. So in general, we have these detectors that are based on the detection of photons, right? And I'm meaning like photons that are really produced by the particles itself. You have other concepts where you're generating charge, you drift the charge, and then this charge generates light. This is not exactly what I'm discussing here. This is really like light that is emitted by the particle itself. And then the two main mechanisms that you need to be aware of, it's basically Cherenkov light, which essentially this kind of like light emission, it's directional. So it depends on the local properties of the particle, but also it has like very, let's say, a specific pattern that gives us information on a track-by-track basis, let's say. And then you have scintillation light, which is isotropic, so you don't have this kind of like very specific information about the particle, but let's say, especially for low-energy physics, you have much more light, so it gives you some sort of complementary information. So in these kind of detectors, these are the two main things that you need to deal with. And then, I mean, probably don't have to tell you, because these are big experiments and I think are quite famous, but like this kind of technology is really everywhere. It's widespread in neutrino physics. We have that most of the experiments, especially most of these very big experiments with huge budgets and, a lot of people working on them are basically optical particle detectors. And the concept in general is always the same. You have some sort of medium, you surround it by some sort of material, basically to isolate this light, right? And then you want to put like photosensors all around the surface, you collect this light, and hopefully you can use this information in order to infer what physics has happened inside of your detector, okay? Some of them are pure Cherenkov detectors, because they use like material that does not scintillate significantly. Some of them are pure scintillators, or essentially, I mean, there is some amount of Cherenkov light, but gets, let's say, overshadowed, or, yeah, I mean, it's very difficult to see because you have a lot of scintillation light. And now there are some new detector concepts that go in the direction of maybe having the two light components, and then, okay, you somehow have to differentiate both of them, right? And yeah, there are many other detectors that I have not mentioned here, but really, this is a very widespread technology. So in order to introduce, let's say, why we need to do things differently, let me talk a bit about what I think it's, things that we could improve in the current pipeline. So, I mean, this comes from my personal bias, like the things I have observed in my experiments, but I suspect that many experiments have these kind of deficiencies in common. So you have one big experiment, and then the first thing that you do is like some calibrations, right? You put some source or like you inject light with a laser, you name it, right? And then you collect data in these very well-known conditions. And then typically each group is a specialist in like one part of this calibration, right? So they have their own random scripts that basically will analyze this data and extract one number, let's say the scattering length or the amount of reflection. It can be anything, right? And then they will collect these numbers, and then you will put them together and then send them to someone that basically tunes some sort of detector simulation that takes these numbers as an input and essentially starts generating realistic events, right? Like now that we know these parameters, we know how to do this kind of simulation. And then with these, because you cannot run Jan4, which is kind of like the software that is used to simulate these experiments many, many times because it's computationally very expensive, you typically calculate some sort of intermediate expected distributions, and then you use these intermediate expected distributions in order to do reconstruction, right? And then finally, after that, you're ready to do physics analysis. So we're talking about many different pieces of software with very diverse expertise, and it's very difficult to actually have everything working together. So this is what I would call, let's say, pipeline fragmentation, right? So you have many different pieces of software, very difficult to maintain, very difficult to understand. If you're a student and you start working in something, it's very difficult to jump around. I think that's really sad. Then we have a lot of effort duplication, a lot of people that's doing very similar things, but simply because they work slightly different. Well, I mean, that's what you have to do. So a lot of human resources just get lost in the technical part of this. And then you have what I would call correlation blindness, right? So let's say, if I'm measuring this kind of, let's say, scattering length, then I have to assume that every other single parameter is known in order to do this measurement, right? I can try to estimate a bit how these things affect to my measurement of the scattering length, but it's not so easy unless like I really have a way of like touching around like the other aspects and the other way around. So if some of these, let's say, for instance, calibration parameters then affect some of the reconstruction parameters, there is an interplay that it's very difficult to estimate there. So what we would like to have, right? So just everything happening in a single framework, right? So just imagine that you could have one framework that is essentially able to do all these things. And then if you have that, then essentially the second point comes from free. It's very easy to tune because you have a centralized framework. And then once you automatize the scripts that is able to process the data of your experiment, essentially, well, you become an expert on that tool. You really can do everything in the experiment. But in order to do this, well, I mean, yes, we need to do, let's say, optimization of all the parameters, but then we really can explore, let's say, the correlations between all these parameters. So this is the concept, right? Like completely different way of dealing with the data in our experiment. Now, let me go into differential simulations with, very simple example, like the simplest I could think of. So imagine that you have some data that is generated, let's say, with some function, in this case, a second order polynomial, right? Well, I mean, if I tell you like that you do a fit of this, well, there are many different ways in you can do this fit. You can do it, let's say, stochastically. Even you can like throw random parameters, right? And then you calculate, let's say, the loss. And then you look what the combination of random parameters really approximates best the data. That's not a very good way of doing a fit, but it's an option. You can do it numerically, which is how you do things normally, right? So you essentially, let's say, you get some parameters, you take like a small step, let's say, a small division of that parameter, you look if the loss is better or it's worse, and then you go in the direction of that it seems that it's improving. But then you can actually do it analytically. So this is the formula, right? Like in this case, you know exactly the formula of your function. This means that essentially you can take derivatives, like explicit derivatives of this function with respect to, let's say, A, B, and C parameters, and then you get new functions. So you know exactly how to calculate the gradients. And once you know how to calculate the gradients, well, you know for a given parameter set, what's the direction in which, let's say, you can go towards a smaller loss, then you take a small step, you recalculate the gradients there, you take a small step, and this is gradient descent. So let's say your gradients are basically becoming smaller as you converge towards the solution, and the parameter values are really converging to the right solution. That's gradient descent there. Nothing crazy. I hope that the idea is clear. Now, I showed a very easy example, but let's look into something that it's much more difficult, neural networks. So neural networks, essentially what you have is a huge number of inputs. You multiply them by a huge matrix, sometimes billions of parameters. And then you have like some functions that basically do some operations after like this multiplication has happened. And then this becomes like the input for another layer and so forth and so on. So you're doing many of these operations, right? This is not a second order polynomial. This is a monster, right? But we can play the same game. So in principle, if we know explicitly like what's kind of like the algebra that goes here, you can basically start calculating the chain rule. And this is what is known as backpropagation, in order to see how much you need to update each one of these billions of parameters in order to essentially start converging towards the solution. This is what neural networks are doing, and now software is getting extremely good at doing this. This is why we have things like ChatGPT, because we know how to do this very nicely. Now, the basic idea here is you can do this for billions of parameters, right? But these parameters have no meaning, and I think that this is a fundamental problem for physics. A lot of people is going in the direction of, let's say, let's have massive neural networks that learn whatever is happening in the detector. We get something out and we believe it, but then we have this problem of the black box. It's very difficult to believe. Now, what I want to convince you is that because we have the machinery that has been built, let's say, to implement these neural networks, we can go either in the direction of having, let's say, ginormous computations that are very difficult because we have very simple operations but many different parameters, or we have a few parameters and then we have incredibly difficult operations because we have nested functions of nested functions of nested functions. This is extremely difficult to calculate by hand if you want to do all the derivatives. But if you have already, let's say, some libraries that are able to calculate, let's say, these kind of derivatives automatically for you, the only thing that you need to know is to define these functions. And then every time that you put some parameters and you calculate some output, you essentially know how to go backwards, right? That's the main concept. So, one particular case, right? So let's assume that we have some sort of differentiable simulation, right? Which is one of these kind of systems where you have these nested functions that takes as input, let's say, some reconstruction parameters. Let's say, can be what's the origin of my track, what's the orientation of my track, something like that. Calibration parameters, scattering length, attenuation length, reflection, and so forth, right? For a given set of these inputs, you can calculate some prediction. You can see how different this prediction is from the data. You can calculate gradients, either for the reconstruction parameters or the calibration parameters. You take small steps in that direction and then you converge, right? So yeah, this starts getting similar. So this is kind of like the fundamental idea of our project, and what I'm trying to show here is like, are we there in terms of like, is the performance that we can achieve really at the level that we can start deploying these things for particle physics experiments? And I will try that, yes, to try that we are there. So our basic exercise consists of, let's say, developing 3 functions, roughly. So one function basically needs to be able to generate many of these rays. Let's say, how are you generating the initial population of photons, right? And then another function will take millions of these photons, and for a given set of detector parameters, we'll find like where these photons end in your detector. And another function will essentially take like the collection of photons that have reached a photosensor and will convert this into an observed heat. And after you accumulate these things, essentially you have an expectation for the amount of hits that you should see, the time that they arrive, these kind of things, right? So yeah, we have a framework that actually does these things, and we're essentially trying to develop these kind of functions just to prove that it's possible. So yes, I mean, we have called it Lucid. So, okay, now here's where like the things get a bit more technical. So anyway, I just want to show the concept, right? So let's say, imagine that you want to model something related to the generation of light, right? And I mean, okay, here you have to code the specifics of your experiment, but let's assume that you have some sort of isotropic light emitter. It can be like a radioactive source. It can be many things, right? But it has some property. In this case, let's assume that the initial time of this source, I don't know, it's something that has some sort of like exponentially attenuated, let's say, time that depends upon a parameter tau. Then what you can do is that for each ray that you're simulating in your simulation, this initial population of, let's say, 1 million rays, you randomly sample, let's say, the time at which it has been generated, and then the way that the way that this photon will get associated basically depends on like this function, right? So it's basically the y coordinate here, such that if you change tau, right, you will get a different prediction, right? So this ray now has an associated value that it's basically informed about the value of tau. And then what you have to do is this kind of games many times. You accumulate all the weights, you multiply all the weights such that the final expectation will be sensitive to all of these intermediate processes, right? Now, okay, this was very simple, but it is actually a bit more complicated in a particular use case because we have actual tracks, right? And then this means that, well, the position in which like these rays are occurring changes with where we are in our track, right? Like the track is stopping. And then, for instance, in the case of scintillation light, you have that you will emit more light depending on like if you have a higher energy deposit, or in the case of Cherenkov light, the cone will collapse as you start like slowing down. So this kind of like smooth local variation, it's kind of tricky to model. So how can we do this? Well, we know the equations, like Jan 4 is able to do this because we know all the physics equations that basically describe this, and you can go and basically go crazy and recode Jan 4 in a differentiable way. That's a lot of work. So another thing that you can do, if you don't have any specific interest, let's say in optimizing the parameters that describe this kind of physics itself, is that you just want to have some sort of like block that allows you to pass through, let's say, the information from the generation point to the next step, something that you can differentiate, and actually it's a black box because we know how this works. So the only thing that we know, the only thing that we need is to code up some sort of function that allows us to go from the generation to the next step. So I will not discuss how you can do the two things. I could argue that, let's say, the scintillation light is easier, so we have focused on the Cherenkov case. So the idea here is that, okay, you can actually use Jan 4 in order to generate some sort of like lookup table, and then that encodes this kind of information, right? Like how the track is stopping, and let's say what's the typical opening angle and these kind of things. So what we did is to generate one package that essentially you can generate many tracks. Let's say, for instance, this would be an example of such tracks. This is an 878 MeV muon. And then what you're seeing here, small arrows, it's basically like the direction of the photons that are being emitted as this track propagates, right? These are Cherenkov photons. So you can essentially use this information to build histograms that will become a lookup table. In this case, our lookup tables are like three-dimensional. You have the opening angle for this photon with respect to the track direction, assuming that the track is perfectly straight. Then you have the distance at which, let's say, this photon has been emitted with respect to the origin. And then you have another dimension that you don't see here, which is the energy. So this is, let's say, a slice for a particular energy. Okay, three dimensions, it changes quite a lot with energy, because as you can imagine, the tracks get longer when you have higher energy. Now we have this lookup table, but we have to make it differentiable, right? Like this is just a histogram. A histogram it's nothing. It's just a collection of discrete values. So if you think about it, this is very similar to an image. A lookup table, it's just like an image, a collection of pixels, let's say in a grid, that have an intensity value. Now an image is two-dimensional, but you can have this n-dimensional. And there is a nice machine learning paper in which they present, let's say, a new type of neural network, which is called sirens, so sinusoidal representation networks, that are extremely good at learning, let's say, these kind of images. So let's say what they want to do is to learn a function that basically approximates this image. So this is kind of like an infinite resolution sort of image, because at any point, let's say x, y, you can essentially predict what's the intensity value. And this is kind of like the image that they want to learn, and this is what they learn with Siren. So we follow the same approach. We have our lookup table for the physics data. We memorized it with something that it's like a continuous function in 3D space. So this is kind of like the input information. This is what we're learning. So this is kind of like evaluating in one slice the function we have learned. And just for clarity, I just like have suppressed all the weights that are very low. So you can see that this is very smooth, nice Cherenkov pattern. So we have a way to say, okay, how likely is, let's say, each photon opening angle as a function of the distance. So now we have the function that we needed. And now that we're able to generate our population of photons, let's say having weights that are realistic according to physics, what we need to have is some sort of detector geometry. So as I was describing before, like there are many different types of detector geometries, and we wanted to do something that is generic, because I mean, if you want to have this type of framework, it's nice that actually works for every single type of detector geometry, not for something in particular. So essentially, we support everything that just like has this kind of like surface and photosensors that are spherical on the surface. It can be very easily adapted to something else, but right now we have, let's say, some way of automatically generating different detector geometries, let's say a bigger cylinder, smaller cylinder, so forth, which I think is very nice, for instance, if you have in mind things like doing the design of an experiment. I think that this is a big problem in our field. Like sometimes you have a given amount of money, and you don't know if you want to put, I don't know, 10,000 photosensors or 5,000 photosensors. But then if you want to have actual performances on how much like the thing would change, it's impossible, right? Because you would need to deploy like a new simulation, retune all the numbers, and then deploy like a custom reconstruction for it. But if you basically can just like change the detector geometry and rerun the whole pipeline, you can get the same number with no effort. So this is kind of like the thing that we're trying to do. So now we know the dimensions of our detector, dimensions of the photosensors, where they are placed. But now we have to connect the origin of this photon population to the sensors that actually are going to be detecting this ray. So how do we do this? Well, here we have to be very careful because unless like you do this calculation in a smart way, you can get like extremely high in computational cost. So the trick is that you don't want to, for instance, do something naive as having, let's say, a straight line, and then you want to look for the straight line to point intersection, because then you have the number of rays times the number of photosensors. So this is like a very heavy calculation. But what we can do is essentially to break this by doing intermediate calculations. For instance, what we do first, if it's a cylinder, is to check, does this kind of like ray will end like in the top cap, in the bottom cap, in the barrel? Then once you know this thing, you can break this kind of like top cap into smaller, let's say, grids. And then you go smaller, such that you have easy operations each time. And in this way, let's say the computational performance, instead of multiplying, just like sums. And this kind of like system to determine this grid is also done automatically for each one of the detector geometries that I was showing to you before. So let's say everything happens on the fly. So we have developed this functionality such that the user does not really need to take care of like all these technical details. Now, the tricky part is that the photons simply not go straight. Like sometimes other things happen. And here's like where actually you have the complexity of like this light propagation. So sometimes you reach the photosensor, yes, sometimes you reach the wall, but sometimes you also get absorbed, or you can change your direction if you have a scattering. So how do we model these things? So in our particular case, we can take that, let's say at first order, we're going to assume that all the rays basically go straight, simply because the typical absorption and scattering lengths that we have are on the order of the detector, right? So let's say 60–70% of the times, the light just goes straight. But then we're going to be, let's say, iteratively refining this kind of calculation. And the idea here is that basically we're going to decide what happens in a hard way. So let's say, for instance, imagine you have, let's say, a photon, then you know what distance has traveled, assuming it has a straight line. Then you know, like for a given scattering length, how likely is it that the scattering happens. And then you throw a coin, and then you say, okay, the scattering has happened, or the scattering has not happened. And then you calculate, let's say, weights according to all of these, let's say, probabilities that basically depend on some fundamental parameters. Let's say the scattering length that I mentioned, or the attenuation weight that I mentioned, or the reflection probability, right? So, I mean, this is a bit technical, but I just wanted to show that it's very simple. This is kind of like copy-paste of our code, right? So let's say you have some probabilities. In this case, imagine that the reflection probability would be the multiplication of the probability of reaching the photosensor times the probability of actually getting reflected or getting reflected, and then the same for scattering. The only thing that you have to do then is essentially to normalize this probability such that you have a vector that adds up to 1. And then you make a decision. Okay, does a reflection happen? Does a scattering happen? This is kind of like a yes or no, kind of like a Boolean. And then the whole trick here is that essentially the final weight that you get, you will subtract the probability and not the probability, such that this kind of weight is correct, but then you're not looking at the gradient, let's say, for the part that you're subtracting. So let's say, in this kind of like tricky way, you can be sensitive to how a variation changes the actual outcome without actually changing the correct normalization. So anyway, my point here is like you have to play these kind of tricks in order to get the right answer, but there are actually ways to like even deal with discrete processes. And okay, now the technical part is more or less over. I mean, I'm going to show you some plots. That's kind of the idea. So, okay, so let's say here, so as I mentioned, this is kind of like a discrete process, okay? So let's say in k equal to 1, you basically assume that you're going forward. And then if a scattering happens, you will calculate like the new, let's say, direction for the photon, and k equal to 2, you will propagate this photon forward. And then if a reflection happens in k equal to 3, you will go ahead. So let's say at k equal to 1, if you do nothing else, you're going to be missing part of the charge, because let's say the 20% or so that should be reflected, you're actually not dealing with it, right? And then, so you have some sort of like kind of like expansion, and then the amount of error that you make, it depends on like how many orders you go in k. So this is kind of like the thing we're calculating here. If k is 4 or 5, simply the probability that you have 4 scatterings or reflections is super low in our detector, so basically you're done. So what we have to do is, let's say, having something like k equal to 6. And you can, okay, you can probably not see it, but let's say the thing looks very similar, but let's say the overall scale of the charge, let's say 10 is here, the Bayesian scale, now it's here. It's a bit different, so it makes a difference in 20% of the prediction also. So actually doing this calculation, it's very tricky, but it's actually very necessary to get something realistic. So how much each one of the different effects that I mentioned affect? Well, this is just to give you a flavor. So let's say this is the nominal prediction. And probably you cannot see it, but okay, there is some sort of shadow here. If you disable the reflection completely, you can see that there is no shadow, right? if you add or not add the attenuation, essentially it just like changes the total intensity of the hits. So again, I mean, you cannot see it because these kind of like bars updated automatically, my bad. But essentially here you can see that this kind of amount of light that you see, if there is no attenuation, of course, is higher. And then the effect of scattering is that essentially you're kind of like not smearing the image. So in the end, like scattering just like blurs out what you're seeing in your detector. So basically you can imagine that you can tune all these things in order to match essentially what you're seeing in your detector. Yeah, right, okay. And now you have like, let's say all the predictions that arrive to the photosensors. I mean, I was showing you event displays, which is of course after making hits, but let me explain a bit how this hit making works. So essentially what you need to have in your detector is a prediction for the charge and the time, right? And then, okay, you have to implement here the exact response of your electronics or whatever you have, but in principle, this again will be a new function where you have the RC or whatever value. There is something tricky about what we do that I wanted to highlight, which is that there is a significant fraction of the hits that do not reach any photosensor. And that's computationally, it's a bit sad because you have done all this effort to calculate these things, and then this photon, if it not ends in some sort of photosensor, it will contribute zero to the loss. So it's kind of like, okay, a bit pointless. And you want the algorithm to actually be aware of like how much it should move a bit this photon to start like actually getting in contact with a sensor and then contributing to the hit. So what you can do is that instead of like having a hard point, let's say this rate just like getting into a very, very narrow point and depositing all the charge there, you can imagine that you can deposit this charge as some sort of Gaussian, such that, you know, the simulation or the loss, let's say, gets aware of like how much changing a bit, let's say, the direction of this photon will change the predictions. So here you can see what happens if you have no relaxation at all, right? You're on top 1, you're outside 0. And here you can see what happens if we have this kind of like Gaussian relaxation. And then, okay, there are some numerical tricks here as well. Basically, we pre-compute this kind of like integral such that it's very fast to do on the flight. Now, regarding the heat making, yeah, I mean, this is kind of like what I was saying before, but let's say you have to implement whatever your detector is doing. So this would be an example of how the time looks if you're calculating the mean time, because somehow your electronics is able to calculate that, or if you're just calculating the time of arrival of the first photon. I mean, again, this depends on whatever you have interest on, but there is no problem in making whatever of these choices differentiable. And of course, something we care about quite a lot is the performance, because the whole point of this is basically to be able to run this many, many, many times. Because if we're going to be running gradient descent, you need to make a whole prediction of how like the event should look like for a given set of parameters. You want to calculate the gradients and you want to update, you want to do a new prediction, right? So we're talking about if you want to have, let's say, one of these algorithms, hundreds of evaluations, right? If this takes, let's say, 1 minute to do one prediction, you're talking about hundreds of minutes. That's probably not reasonable. So if you want to have something that really optimizes, let's say, in order of tens of seconds, you really need to have these predictions and the calculations of the gradients in the order of like milliseconds. This is very, very fast because it's a lot of operations for millions of photons. But here you can see the performance is actually super fast. So if you have something like 100,000 photons, essentially you can do this prediction in something like 2 nanoseconds. 2 milliseconds. So you can imagine that here we could do like many, many predictions super fast. And actually, when you look at like what's the timing, not only for doing the prediction, but also going back and calculating the gradients, you have, let's say, a factor 2.5 overhead. So, okay, I mean, it's something, but it's not really dramatic. So again, you have order milliseconds. And then what you can do, let's say, during optimization is that you start doing some prediction that it's very coarse. You start with like a few photons just to get like more or less on top of like the region that you actually expect to have the solution. And once you're more or less very close, you can increase this number of photons quite a lot, such that you do like the fine tuning of, finding the exact solution. So this in principle can be done very, very fast, like in order few seconds, maybe tens of seconds. And yeah, I mean, when I think of this is that, I mean, this is with the current hardware. I would assume that in 5 years, 10 years from now, we really can push this further quite a lot. So we are still technically limited in some aspects, but really we're at the edge of like being competitive.
Sorry, César. These numbers, the time that you need,
yes,
depends on the complexity of your detector or not.
So the main things here would be how many rays do you need to simulate in order to get, let's say, a prediction that it's stable in terms of like
the number of rays.
The number of rays and the number of photosensors. So it scales linearly with both. So if you have twice as much photosensors, it goes factor 2. But this is 10,000 photosensors. So and 10,000 or 20,000. I cannot remember because 10,000 is SK, 20,000 is hyper-K. So maybe it's one of the two. But
so if you have like, a detector where photons bounce 1,000 times, it doesn't matter.
well, if let's say getting right the prediction of like you need to like compute 1,000 times, that's essentially K. So K here is telling you to how many, let's say, expansions or let's say scatterings you need to take into account in order to get the right solution. If you have that this happens tens of times in your detector because your medium is, for instance, super dirty, probably you want to do another approach. Again, you can probably find some sort of like way to approximate what's happening, kind of like smoothing, because in that regime, you're already entering something that it's maybe easier to estimate the mean. So you can kind of like instead of doing it photon by photon, you can try to smooth out like the prediction having some sort of effective functions. But yes, so this is working under the assumption that you have very transparent media or something like this, in which most of the photons go straight, and then you have a fraction that actually undergo these kind of like more complicated things. But yeah, I mean, that's more or less the idea. So, okay, so if we want to validate these things in realistic conditions, then we need to generate some sort of like fake data, because otherwise it's going to be unrealistically good. So you can do the same thing that we were doing before. So as I mentioned before, in this kind of events that we're generating, before we were basically storing these things as a histogram, kind of like to average many of these muons. But what you can do as well is to store like individual photon information. And then this individual photo information, basically you put it inside of your detector, and then you retrace each one of these initial photons, right? So this is really data-like. And then here you're taking, let's say, all discrete operations. So just exactly as it would happen in detectors, let's say you have hard reflection or you have hard scattering, these kind of things. And then you can see here, let's say, some examples on how it looks, let's say, for one, well, the quality is not maybe the best, but maybe this one is the one that you can see better. This would be a data-like event where we're, let's say, injecting one of these muons inside of our detector. And here would be, let's say, the associated smoothened prediction that you would get, let's say, for the average event with these initial track properties. And you can see it's very easy to actually run in different detector configurations. So calibration. So let's imagine that, for instance, you have some sort of isotropic light emitter. This is something we don't super K, so this is why we're following this kind of example, in which you have in your cylinder some sort of like ball that it's just emitting light. Then you can calculate what sort of like output you should see. Okay, in this case, statistical fluctuations doesn't matter because you typically have a lot of light, so typically you get something very smooth. You could also look at time. Depending, in some cases, it can be interesting. Typically here, what mainly matters is, let's say, the charge. And then we can start doing like some sort of tests, right? Let's say, imagine that you want to be looking at, let's say, you do one-dimensional scan if you vary that parameter. So let's say, imagine the scattering layer. Let's assume it's 4 meters because this was a smaller detector for, anyway, some other reasons. And let's say, imagine that you go slightly off the solution in one way. Let's say you're doing the scattering length smaller, or you're doing the scattering length higher. What you want to see is that essentially for smaller values, you have gradients that are negative. For higher values, you have gradients that are positive. Such that when you do an update that it's, whatever value you have minus the derivative, you're going to be pushing this, let's say, towards the right place. And yeah, this typically corresponds to having a loss that it's well aligned with, let's say, has the minima at the true solution. And you can see that for the 1D, like all of the things really have very well aligned, let's say, gradients pushing towards the right solution. Of course, you have to look as well into the correlations. So this would be, let's say, how the scattering length relates to reflection rate, the scattering length reflects to attenuation, but you can see that, okay, maybe the graphics are not so great in this screen, but here you can see that essentially the darker means that this is the minima in terms of the loss. And these kind of like arrows that you're seeing are kind of like the gradients. So this is basically how the gradients are basically pushing you towards the center wherever you are in this two-dimensional space. You can also look at like higher dimension, but it's a bit more difficult. And then I think that
in a multidimensional space, they converge all to a single point.
Ideally, yes. It depends. Like also you can have, let's say, some sort of conditions where you have, let's say, some degenerate solutions or local minima, and then it's a bit more tricky. But then you need to find like an optimizer that's basically able to explore this kind of like complex minima, complex loss surface in order to get to the true minima. But so for instance, in this case, what we're doing is to have a quite fancy optimizer that basically has some sort of population of points that we're evaluating. And then, well, I can give you more details if you're interested, but let's say it's kind of like a combination of a traditional optimizer with the grid information, because basically you're using the local covariance in order to see how you should sample the new points and then you evolve and so forth.
Okay.
But essentially, the kind of test we're doing is like, okay, let's imagine that we do like a tiny perturbation to the right solution, one perturbation that is not so small, another that it's really very hard, no? And can we optimize all the parameters at the same time such that we get to the right solution? And yeah, the answer is yes. So let's say most difficult case, let's say it's the purple one. So you can see that actually the scattering length is really very far away at the initial point, and it's true for the other parameters, but it really converges to the right solution for all the different parameters. And this makes sense. I mean, for the calibration data, essentially you're benefiting from having the very high stats of like all the sensors having correlated information. So in principle, you should really get very, very nice precision into the final parameters. What about reconstruction? Okay, so let's imagine that all the degrees of freedom for our track are basically the origin, is YZ. Then we have two angles, right? Phi and theta, and then we have the energy of the track. So just like to make things simpler, these are like the same 2D plots that you were seeing before. For the energy, this is not so clear simply because this kind of like scale is much larger, and we should have rescaled this such that it doesn't look that this is a flat line. But it's actually more like this if you rescale it properly. That's my bad. But really, again, like the gradients are really pushing you towards the right solution. Yeah. So, but you need an initial guess. So how you can do some sort of initial guess? Well, I mean, you can explore many options. I'm sure that SuperK has their own, but here again, we're benefiting from having ways that allow us to calculate the loss very, very quickly. So for instance, what we're doing is to calculate 50,000, let's say, random events, right? And then we cache these events. And then at the beginning of our reconstruction optimization, we load all of these into memory. And then we're going to be calculating, let's say, the data event loss to each one of these 50,000 events. Then we rank them. This takes, yeah, like it was 2 seconds or something like this. It's really, really fast. And then essentially what you can do is to do some sort of average of the parameters of the best ranking solutions. And you can study like how many of them you have to average in order to get some sort of optimal guess. So for instance, if you average 3 events or so, you typically are making a direction error on the order of, I don't know, 5 to 6 degrees, a position error on the order of 5 meters or so. This is for Super Kamiokande, by the way. So you have that the total size is something like 40 meters times 40 meters. So yeah, it's a big detector. Of course, the bigger the detector is, the harder this problem gets, but we get a pretty decent, let's say, initial guess. So the first thing that you want to do is to see, can you be able to do this gradient descent? Well, you have, well, let's say the data that you want to optimize is actually a prediction, right? So you have no statistical fluctuation, something very, very smooth. So this is kind of like a closure test. And yeah, sorry, I did not have like a better video than this, but you get the idea, right? So you start somewhere and then you start like comparing the thing, and then it really starts conversing very smoothly. And then you essentially want to do the same for the data. So yeah, my cluster died yesterday, so I could not fetch like the best plots for this final part of the presentation, but essentially here you can see 10 different events that essentially all of them are converging to the right solution. Probably I should have waited a bit more there, but you know, like everything really converges to the right solution for the closure test. So this is trying to guess, or let's say trying to reconstruct prediction-like events. Now, a much more difficult process is, can we actually do the same for things that are data-like events, where you have all these, let's say, noise variability. And then the first thing you have to do is, again, you look at the gradients. The gradients look good. You can see very well aligned. Let's say all the points are crossing 0, very close to the actual solution. Let's say both when you're looking only at the charge part of the loss, that it's basically just like, let's say, a log likelihood Poisson loss, or the time, that in this case, okay, we have mean time, but anyway. And here you can see one specific data example. So let's say for visualization purposes, I think I was cutting all the hits below 5 charge units, which would be all around. So this is quite more messy than it looks here. But here you can see like how accurate these kind of things are. So you're basically converging 65 centimeters and like 2 degrees. And it's very difficult to tell apart like the blue, that would be, let's say, the outer edge of like the cone at the initial position, and the red, which is the one that you're guessing. So yeah, so we're still in the process of like actually, let's say, refining this optimization process. We think that we can do better. This is kind of like the part of the project that we're missing to wrap things up. In the case of Super Kamiokande official reconstruction, just to give you an idea, they claim they have something like 15 centimeters in average and around 1 degree or so in average. Yeah. And And yes, we're still a bit far away from that. We have something like 50 centimeters and 1.5 degrees and so forth. But still, like it's there in terms of order of magnitude. Now we have to like really refine the optimizer to get to the right solution. But once you basically achieve something that is comparable, then you're done. Essentially, you have demonstrated that this thing can do exactly the same that SuperCameo can do or any other experiment does in terms of calibration, in terms of reconstruction, with the added benefits that I was discussing at the beginning. And with this, I come to my conclusions. So hopefully you have been following, let's say, kind of like my argument that this thing is kind of like very powerful and really enables new ways of, let's say, doing the computing part of our experiments. In part, this is really benefiting from, let's say, advancements in accelerated hardware, let's say, massification of GPUs, they're becoming super cheap, plus all the libraries that are being developed, let's say, for all the AI-related projects, not only in science, but like everywhere. In this particular case, I was talking about one particular example for this application, how you could use this to develop this kind of like calibration or reconstruction, let's say, framework for these neutrino experiments. But again, you can do this for absolutely any detector as long as, you determine what are the parts of the problem that are actually difficult to differentiate on, and then maybe you can apply some sort of approximations. There is people that has used these in the past for liquid argon TPCs. So, I mean, we took the idea, let's say, from there. This was the start of the project. Essentially, they did it only for calibration, but here we're doing calibration and reconstruction as well. But this is just to say that you can do it in other experiments as well. So yes, there is some sort of open source code where all the things that I have been showing here are basically available for whoever wants to play with them and really getting a better feeling of like how these things work, or starting, let's say, maybe some project from there. The status of the Git repository now, it's not like the best because we're doing a lot of, let's say, development, but hopefully in 1 2 months, we will have, let's say, a nice list of, let's say, notebooks that you can run and you really get like all these nice plots such that you really can play a bit around like with the detector geometries and these kind of things and learn how this works. And yeah, I mean, once we have that, essentially, hopefully the paper will come at the same time where we really explain all these things at length and you actually can read it. You don't have to rely on my explanations. So yeah, I think I mentioned everything other than, okay, if you really have some interest in differential simulations, either for detector modeling or any other thing, you can use it essentially for anything that we traditionally would do with some sort of fitting. Just like drop an email to either myself or my close collaborator, Omar, who has been doing half of the things that I have been showing here. And yeah, we'll be very interested in seeing how these can, let's say, branch out to other domains and how we can make it grow. So that's everything. Thanks.
Thank you very much. Well, I have a couple of questions, but let's take questions from the audience first, if there are. Frances?
So, about the reconstruction, can you explain that a little bit better? Because
yes.
I mean, how do you do that? You have the list of parameters typed from the simulation, and then you use those parameters to reconstruct. I mean, what?
Right. So let's see. Maybe let's go to the very beginning because I think the best is maybe even this slide, right? Sorry, what am I doing? Yeah, this one. So conceptually, right? So as we imagine this, let's say, okay, so in this particular case, I'm showing some event display for one track, but you have to imagine that first you would have, let's say, a pre-step where you actually are looking just at calibration runs. And then, okay, in calibration runs, you actually don't have any sort of these track parameters, right? You code up something much simpler that it's okay, the origin is fixed because we know it and you don't have to get like any parameter from there. This is well known, or you can also optimize this at the same time, but that doesn't matter. But essentially you use those calibration runs in order to just like optimize the calibration parameters, right? Oh, this is the scattering length and you figure it like that completely. Once you know the calibration parameters, then they are fixed. You're not going to be touching these parameters any longer. And then you're going to be looking at these other, let's say, physics runs. And then for these physics runs, essentially, yes, you can throw a prediction, right? You compare it to the data, and you're going to be doing optimization just on this physics parameter. That's kind of the idea. I don't know.
So basically, you have to do like a likelihood with you have to run several predictions to compare with your data.
Right. So okay. So in particular, let's say, so this is just the forward. So you input, this is kind of like, yeah, so this is like a simulation, let's say like Janford, right? You input some parameters that describe the conditions of what you believe has happened in the detector, and then you get a prediction. Then you compare to the data, but then you have to define some sort of loss. For the loss, you can try so many things, right? But once you have this loss, essentially you can go back. Yeah.
You have to launch several predictions will take a lot of time, right?
Right. So this is what I was then trying to explain, let's say, in this kind of like performance slide. Yeah. So the scale here, you cannot see it, but this is milliseconds, okay? So let's say you start predicting very few photons because you don't need to have like these super detailed predictions when you're far away. I mean, you can see, okay, this ring, it's really nothing close to like what we have, right? So you can start somewhere here, and then you can do a prediction in like order of, I mean, with the gradients, let's say in less than 10 milliseconds. So 100 predictions would be 1 second, right? And then you can really get very close to the actual solution.
You need 1 second to reconstruct one event.
No, I mean, not really, because then you want to get detailed, and then, okay, this is for k equal to 4, we are using k equal to 5 or to 6, so maybe the line was a bit higher, like this. But let's say the idea is to have reconstruction for sure in less than 1 minute, 30 seconds. That would be the game. Yeah. I mean, this is also one of the motivations, because the current reconstruction algorithm, it's really reaching the end of what's computationally feasible for hyper-K.
So with neural networks, it's longer than that.
No, with neural networks would be actually faster. Because with neural networks, you can jump directly, let's say, from some conditions. So there is a paper on something that does exactly this, a network that is called Cringe. But essentially, you input the parameters, and directly the output of the network is directly the event prediction. That would be super fast. Yeah. But then this network has been trained with like some parameter conditions. Let's say the prediction that it does, it's for a frozen scattering, for a frozen everything. So you don't have no control. If you want to change that, then you have to retrain the whole network, which is very expensive. So for each run of the experiment, you would need to do it again. And also that's not providing any way of like, let's say, doing inference for all the other parameters. So that's a bit of the problem.
Yeah, the question I had is that for these kind of like water Cherenkov detectors, it works very well, obviously. But the limitation I see is that obviously you don't have any control on the gen parameters.
I mean, okay, so in principle,
You want to have it.
Exactly. So in principle, if you would have, like, say, very specific interest in, like, I don't know, some jump for parameter, let's say, how often you have inelastic interactions. It can be anything, right? You can actually, instead of using this kind of trick where we basically bypass, let's say, all the jump part by basically having a network, you can code up like all the equations.
Yeah.
And then, yeah, you ignore all the parameters that you don't care about, like they are treated as fixed, and you look at the one or a few that you're interested in, and then you can do the same kind of study. But this goes more in the direction of like almost doing physics with this kind of like system, because that could be your measurement. Like this is, if you can do it. But if this is, let's say, very deeply embedded in a chain of, like, say, physical processes, you will need to write a lot of equations.
No, of course. Yeah, exactly.
So it's that's the annoying part. That,
yeah. No, the thing is that, like, at least from the simulation point of view, Gent is now essentially the bottleneck.
Yes.
So optimizing that would probably have a bigger effect on the total simulation time than doing it for the detector simulation part.
Right. Yeah. I mean, it really depends on like how many things you want to put in from them for, right? Like, I mean, I'm sure that you can always play some tricks. So as long as your problem is, let's say, narrow enough, you can probably just like factor out the things that you don't care in something that is relatively fast and stable, and then have some sort of like correction for like the part that you care about and optimize it in this way. I do agree. Like, if we're talking about can we have differentiable Jan4, this is not going to happen anytime soon. I think that this is honestly the direction the field will take in, I don't know, 15 years. It's very difficult to make a prediction. I think that if you would have something like Jan4, exactly Jan4, but then you can compare to data and say like, okay, now optimize the Jan4 parameters, people would love it. This would be unbelievable.
Yeah, I know there is some effort this Celeritas thing, but I think that's only...
I haven't looked much into it, but yeah, I have...
I think it's only GPU accelerated, it's not differentiable.
I think that there is like some sub-team within Jan4 that is starting to think about these things. But the problem of Jan4 is that, I mean, it's a multi-purpose tool for the whole community. So
Yeah.
I think that for them, it's kind of like overwhelming. If you want to do this, let's say in one giant step, it's a massive effort. You have to commit and then you have to put lots of.
And also it's like, maybe it's even faster to just rewrite everything.
No, I mean, I think that at that point it would be Gen 5, right? Like it's a completely different thing. So, I mean, to me, that was kind of like the interest on this project. Let's say you probably will not jump and have something like Gen 5 that is fully differentiable. You first need to see some sort of community-driven effort where like some people showcases that actually this works very well in some cases.
Mm-hmm.
And then you build some sort of like case to say like, okay, these are the motivations, right? Like some experiments are already using it. Instead of, let's say, putting the effort on the community, let's have, let's say, some support from CERN or whoever wants to put money to hire people and do it. But
right. Yeah. Then the other comment was more like, haven't these problems already been solved in the field of video games?
Right. So
like it's very, very similar to what
the
video game needs to do.
That's actually extremely true. Like for instance, ray tracing in video games, it's something that happens all the time. So a lot of like say the ideas that we have are borrowed from them. Something that they don't care about in the video game industry, it's first of all like the quality of the gradients. Like many times you can play tricks in ray tracing just like by taking non-discrete operations, right? And here we have, the other problem is that we have quite a lot of, let's say, discrete operations, like for instance, scattering, attenuation, and so forth. And it was quite a challenge to see like how we could not kill all the gradients by actually having these things. So I would say that this is the main difference in the emphasis. They want to have something very fast that goes forward, want to have something very fast that goes forward and then comes backwards.
Yeah.
And just in that direction, let me add that actually, so this project is written in JAX for whoever is familiar with it. But then we actually started the project doing it in some language called Tai Chi. So Tai Chi, it's actually some sort of like industry tool to exactly do this kind of like ray tracing. No? So we were like, oh yeah, it's great. Let's use like the tools from the industry. The problem is that you have very little control. Let's say if you want to extend some functionality in Tai Chi, it's extremely rigid. So at some point it was a bottleneck and we decided to, throw it away, start from scratch. But there is a lot of interesting tools out there that like industry is using, and I agree that it's very nice to not think in our kind of like high-energy physics framework, but like really see what kind of like other communities that have a lot of money and resources are doing in a smart way. It's just that sometimes we have different motivations that basically make everything that they do useless. But yeah, sometimes the ideas are good.
Yeah, I thought about this because I guess there are a lot of like the problem of the intersection of a ray with the solid.
Right. So for all these tricks that we're playing, like this kind of like grids and these sort of things, these are really many tricks that
like
they
super
use for these things.
In those
I mean, this is why it's so fast. Like the fact that we can reach, let's say, millisecond level predictions for millions of rays in tens of thousands of photosensors, it's really because, there are many tricks that actually work very well because, it has been developed for video games. Yeah.
Okay, any other question? No. I had another question about doing this, like, and the thing you haven't taken into. Somewhere, yeah.
My question is like, I saw you doing this optimization work on single events, but does it happen also for distributions and I don't know, like if you want to optimize a spectrum or something like that? If you want to optimize the parameter to get a spectrum?
It can be absolutely anything. I mean, there is no limitation. So let's say, here I'm talking about hits as kind of like a hard charge prediction. Let's say, I see like 5 charge units or something. But if you have a spectrum because you have like a time waveform or something like this, then in principle, you can build a loss that it's, let's say, waveform aware. Right, you can compare, let's say, this waveform at different points in time, and then your loss would be, you can have some parameter that describes, let's say, this kind of like spectrum, and then this would be a new parameter that you would be optimizing. So there is no limitation.
Okay.
Yeah, the other comment I had is that at the moment you don't take into account the wavelength at all.
Right, smart. Yes, so at this point, essentially, we're taking all the photons from Gen 4, and then we go forward. There are some refinements. Like, so if you would like, let's say, let me put it in this way. How far we are from actually using this in a real experiment, right? Like all these nuisances, like wavelength, it's one of them, but there are a few. It's pretty tricky. And I would say it's 5-year effort of quite some people. Like you need a group to do it because it's very difficult. So we're kind of like ignoring all these problems. But regarding wavelength specifically, essentially you have that you could simulate it. Like this would be a new random number, but actually you don't need to differentiate through it because, I mean, you know that the Cherenkov, it's basically kind of like exponentially distributed in wavelength. And then, for instance, what you could do is that this random number that each one of the rays has associated then has an impact, for instance, on the PMT. So you can have a quantum efficiency that is, let's say, wavelength dependent.
That I guess it's easy.
So it would be one extra layer of complexity.
I was thinking more about like the scattering length depends.
The same. So once you have associated this wavelength, then the scattering becomes, let's say, wavelength dependent. It's just that, if you want to do everything very detailed, you have to build on top, build on top, build on top. This is kind of like a first step. But I think that once you see that there are no fundamental, let's say, limitations in each of the steps, let's say, individually, then just like extending them. I mean, to me, conceptually, it's like, okay, I mean, yes, it's work, but it's not that it's going to fail. You have to do it.
No, because I was already thinking about doing this for next. But
it's very similar to what the RTPC people did. The only thing that then you would need to have, let's say, some information for, well, I mean, it depends on the energy that you have, but you could have the track and then you have to drift it first and then you put the response. I mean, it's doable, right?
In our case, the thing is that we have like reflections that depends on the wavelength.
For the S1.
Also.
Right.
Wavelength shifting, we have. It's more complicated.
I mean, yes, I think that like once you have that, you have to model the transport itself and the process, it's, let's say, in the statistical limit where, like, for instance, you have diffusion in the electron cloud, these kind of things, then you have to change a bit like the approach. You cannot model electron by electron. You probably want to model, say, the statistical properties of the electron cloud, right? These kind of things, but
For the diffusion, we will have that, and that's why I was asking before, if you have more bounces. Because in this, most of the light
will reflect more than once.
Right. So actually, okay, so let me go quickly in that direction. So this project actually has like two branches because we started, let's say, thinking in this direction because, okay, some history, but I think it's important in this concept. So these ideas arise like in RTPC, and then they have like some sort of experimental constraints, and then they said like, okay, let's extend it to like what Cherenkov. But then we started working on it and we realized it's very different. So we had this kind of limitation. So the two approaches that we explored, it's like, one, it's what we call the analytical solution. This would be the analytical solution because you're explicitly trying to model all these functions. But there is a full neural network way of do this, which is essentially what they do. It's super cool. And actually, this is something that they're trying to push as the standard, let's say, reconstruction for WCT. So the idea is the following. How can I explain it fast? Let's imagine, okay, so in this calibration example, right? Let's imagine that you have some sort of robotic arm in your detector, right? Where essentially you have this position, you have tens of them, right? Then in principle, you can have a neural network that basically learns for this point, what's the actual expectation for each one of these photosensors. And this is convolving every single reflection, right? It's just like a probability. If you have these at many different points, then essentially the only thing that you need to do is to interpolate. And then essentially what they have is a function, in this case, it's a huge neural network that you input where you are, and it gives you directly a prediction of the thing. But then you have control in that sense. I mean, so you can have, let's say, one first network that actually we borrowed from the other project. So let's say this first network, this first network, it's just like to determine like what would be the positions of your initial event within the detector, and then the second network will translate this into expectations for every single photosensor. And in this way,
one at the end is like an multi-dimensional interpolator.
So in that sense, exactly. So in that sense, you could do it in that way, and you don't need to put any equations. But if you have some intermediate physics that you want to model, maybe you can break this into even one more step. But yeah, I mean, I think that this is very promising as well. And in this way, you get rid of all the complications of these 100 reflections.
No, it's actually interesting maybe for optimizing the PET design. If we think about it.
We can probably stop here and discuss.
At lunch. Okay.
Should I close this? Yeah.
Probably you can just stop it if you want. Yeah.
1 hours. Okay.
Okay, we can thank the speaker. Thank you very much. You can continue at lunch if you want.
Yeah, of course.
Sí.
¿Qué le pasa a este?
Está peligroso.
Se ha dormido,
Había un insecto aquí para...
No, pero así no. Ven así las haces, ¿sabes? ¿Ya vamos nosotros?
Sí, sí. Reservado en el Lucas a la 1:30.
Hasta luego.
¿Tienes a comer?
A mí no me habéis invitado.
¿Has invitado?
¿Estás invitado? Ahora estás invitado.
Ahora no puedo decir que no. Como joder.
Quería hacer el...
No
me habéis invitado.
A mí tampoco me habéis invitado.
Vale.
No, nosotros 4.
Estás
¿Quieres venir a comer?
Sí,
Son 20 pavos.
15 pagos.
15 pagos. Que no, que no. Vale, yo voy a dejar, sí.
Quedamos... Me quedo con el boy y hablo de algunas cosas. 10-15 minutos.
10 minutos donde...
Nos vemos aquí.
Si no te importa...
Vale, sí, sí, lo digo yo. Y voy a dejar esto y va.
Gracias.
Van, suben y bajan. O sea
Sí,
que...
aquí, nos vemos aquí.
Sí. Nosotros quedamos aquí dentro, entrar y ya está.
Vale.
Hasta.
Ahora, no, hombre, lo de la simulación es per una banda. I també per citats. Tenim que pensar a veure si podem fer alguna cosa. El tema és que, o sigui, jo no sé, en el nostre cas de Next, o sigui, nosaltres pensem en Next, tot això que estàs dient, ho fem old style. O sigui, el que fem és...
Sí, com tots els experiments al mateix.
Bueno, no, però vull dir, això que estàs dient de parametritzar la resposta i tal, que nosaltres el que fèiem són el que diem taules de llum.
Sí, lookup tables.
Lookup table.
El Siren aquest, t'ho puc passar, hi ha un paper d'Icarus, on ells bàsicament utilitzen això ja directament amb el... Sí, i això ja s'ha fet.
Sí, no entenc molt bé la diferència entre això i que tu estàs proposant. O sigui, al final,
No, val, o sigui... Clar, o sigui, no, simplement, això és la segona part, exacte, o sigui, això seria el lookup table, bàsicament, no té més.
Jo gasto per crear els lookup tables.
Exacte.
Sí,
això de fet és el que fan, de moment, la gent de l'RTPC, amb els que col·laboro i amb els que va començar el projecte, ells van començar així, o sigui, fent differentiable lookup tables, fin, ja està. El tema és, bueno, tota la resta ho pots fer o no ho pots fer, però si vols fer només això és superfàcil, ho pots fer en una tarda.
Bueno, en el nostre cas, el que està dient Roberto, tenim tota aquesta absorció per el TPB, la reemissió, els rebots...
Però si no t'importa, en el sentit de que tu vols acumular tot i no poder dir quan ve d'aquest efecte i quan ve d'aquell efecte, però simplement tu vols acumular tot i fer una predicció,
No, però sí que tenen aquests efectes.
No, vale. O sigui, el tema és, a través d'aquestes lookup tables, tu pots fer en dues formes. O sigui, una de les formes és bàsicament tu simules un jump for, tens en compte tot i llavors calcules. L'altra forma és això. Tu tens dades de calibració, sources all around, però bàsicament fas data-driven detector response.
Sí, això ho fem per simulació, però també vols... Al final, una cosa que és important moltes vegades és comparar la simulació per estar segur de que entens que està parlant de detector.
I això és la putada si només vols fer data-driven amb el lookup table, que llavors, en aquest sentit, aquest tipus de solució tens com el control de pots veure cada un dels paràmetres més o menys i si s'ajusta amb el que tu t'esperaries. Tens un scattering length enorme, raro, saps? Però sí.
I una altra cosa que hi ha un problema, almenys en el nostre tipus de física, i jo penso que s'aplicarà també a altra, que és, tu a l'hora de dissenyar un experiment, moltes vegades dius, fas 1 metre, fas de 2.
Ja, correcte.
Però, clar, de vez en quan dius, tinc espai per a 5 o 6 metres, però la següent escala seria de 1, no? O de 1 i mig, no?
Sí,
Què faig, no? O què proposa?
sí.
I això normalment, si vols fer un càlcul de sensitivitat d'experiment
Sí,
i tal,
sí.
hi ha coses que no són lineals.
I és superdifícil, no? Sí, sé com va.
I no sé si aquest tipus de coses se podria, més enllà de la llum, no? De dir, bueno, jo fique tots els efectes, els backgrounds sobretot, no? Fique els backgrounds, fique la senyal, tal, i calcule el mínim o el màxim, com vull dir, no, perquè el màxim de dir, com més gran és el detector, normalment millor, però calcule el gradient i dic, bueno, que estigui plegant a aquesta regió on el meu gradient ja, el seu detector el doble de gran.
Sí, exacte, ja és igual.
I llavors sé que la versió òptima a dia d'avui és esta, sí. Este tipo de tecnologia se podria aplicar a esta estimació dels backgrounds o dependències en la geometria, el tamany del detector, més que geometria.
O sigui, el tema és que, clar, com està tot integrat, és superfàcil de canviar alguna cosa. O sigui, tens que tenir tot el background funcionant. Però com funciona? Tu pots anar i dir, vale, ara, en lloc de fotre amb fotosensors distribuïts uniformement a una pel·lícula de mi, ¿Con esto no hace falta?
Ese antes.
No sé, no está bien.
Antes, vale.
No, no.
A ver si sabes. Porque una vez con la obra esta no ven el letrero. Vale, vale, vale. Estamos perdidos.